Hi, everybody. Today we are going to be recording Dynamics Lecture 21, which will cover Section 15.3. And the topic of Section 15.3 is called the Instantaneous Center of Rotation in Plane Motion. Now, when we talk about the instantaneous center, the slides that we're going to be using from the PowerPoint that's posted to your Moodle page are 22 through 28. So what I'd like to tell you, first of all, before we get going about ICR, which stands for Instantaneous Center of Rotation, is that this is a technique for problem solving. In other words, you never have to use ICR, but sometimes, you do for your homework, but in real life, you can always solve this using vector math cross products, but this is a shortcut. And for cases where it works, you can greatly simplify the amount of work that you have to put in by using this technique. So what it basically, the principle behind ICR is that every point, the plane motion of any point on an object, such as this attractive slab o potato that we have drawn, can be thought of as a translation plus a rotation. So in other words, if we think about point A translating and then a rotation of point A, we can come up with something that is the total velocity of point A. Or we can think about another point B somewhere at which we have a translation of A plus the relative velocity of B with respect to A. So when we divide up the motion into a rotation and a translation, we can also think about this velocity as being the slab, every point on the slab rotating about some point. Now that point, which is shown here as being point C, there's no reason that that point would be on the slab. But remembering that omega cross r is equal to velocity, and that's a total expression of the velocity, if we had an r that represented a point about which all points at that instant are rotating, then that cross product, omega cross r, would represent the total velocity of the point. The trick is finding the point. And the trick that you use to find the point is the fact that in order for the total velocity to express that way, that r cross omega is going to be 90 degrees, or in other words, it's perpendicular. So if you have velocity vectors at two different points on a slab, A and B, and you draw a perpendicular to both of them, wherever they intersect is going to be the instantaneous center of motion. Now, at that point, when you find out that r, you can say VA is equal to omega crossed with r, which is the distance from C to A, and from B to A. So the total velocity of those points are both going to be different. The r's are going to be different, and the omega is going to be the same. Now, it's important to note that this only happens for one instant. So in other words, the instantaneous center of motion changes over time, and it will follow a locus of points that we'll talk about a little bit later on. But if you have a velocity vector of two different points, you can determine it using this technique. So the slide here just outlines the process. If the velocity of the two vectors are known, then the ICR lies at the intersection of those points. Now here's another point. If the velocity vectors are parallel, the ICR is at infinity and the angular velocity is 0. What that means is if A and B are parallel to each other and have the same magnitude, there is no instantaneous center of rotation, because what we're really talking about is not a rotation at all. It's just a translational motion. If the velocity vectors at A and B are perpendicular to the line AB, then the instantaneous center of motion lies at the intersection of those points and the one joining the extremities. So here, A and B both have parallel velocities, and yet the velocity of A has a different magnitude than the velocity of B. So you can do a geometric construction where you draw a line perpendicular to the points joining A and B. You just draw a line, perpendicular to the vectors VA and VB through points A and B. In other words, the points that we're talking about. And then if you draw this to scale, you can draw a second line through the tip, or in other words, to scale, and that will also be the instantaneous center. So the important point to note is that this is a technique. It only happens at one particular instant. The instantaneous center of rotation changes instant by instant, but in the instant, if you have this information, then you can determine those points. You can determine omega, and you can determine velocities at other points very, very quickly. All right, so here's an example. These are the types of problems that we have worked in the past. But here, if we have a velocity of b and a velocity of a, we draw a perpendicular to the velocity of b, we draw a perpendicular to the velocity of a, and that point is the instantaneous center of rotation. So what you can see here is we're saying that's equal to VA, which is that velocity, over that perpendicular distance, AC, which is L times the cosine of theta. And then once we find that information, we can also find the velocity of B. So that's a lot quicker than the technique that we used before. The technique we used before is the one that will work every single time. But if you have enough information and it's quick enough to put graphically and to scale, you can solve this extraordinarily quickly. So some of the facts then: the velocities of all particles on the rod are as if they were rotated about c, right? So that means we know what omega is, and once we have omega, we can use that with the perpendicular. If this velocity is going to be at some other angle, isn't it? In other words, this is purely vertical, this is purely horizontal. Everywhere here, the direction is going to be a little bit different, but we can use that same principle, and we know that the instantaneous center at that instant is still going to drop through point C and will be perpendicular to that velocity. The particle at the center of rotation has zero velocity. Okay, if it's on the body, that becomes very important. Otherwise, it's just a fact. Because why? Because velocity is equal to omega cross r, and if it's through the center, r is equal to 0. Therefore, the velocity is equal to 0. Now here is something about the way that motion moves. The motion of point C. The particle coinciding with the center of rotation changes with time, and the acceleration of the particle at the instantaneous center is not 0. Right? It is the instantaneous center of rotation. It is not an instantaneous center of acceleration. This only works for velocities. So the next point, the acceleration of the particle in the slab cannot be determined as if the slab were basically rotating about c. Only works for velocity. That's all it's saying. The trace of the locus of the centers is the body centrode, and in space is a space centrode. Okay. That is not as important. Sometimes they want you to determine what it looks like, but it's not that important. Now here we have that same kind of a problem that we worked before, where we have a double roller rack and we have a velocity of a. This is the kind of problem that anything on a wheel really lends itself well to instantaneous center of rotation solutions. So here at point D, we can determine, we have a velocity at point B, we have a velocity at point A, so you know that the instantaneous center is going to be found by drawing a line through A and B, and that's perpendicular to the velocities, and then we attach the tips, and we have the instantaneous center. That means that the velocity at D is going to be perpendicular, so if we can find this length, we can also find the magnitude of the velocity of D. All right, here's another problem that's going to lend itself kind of nicely to that solution. Just skipped ahead. Sorry about that. We did this too, where we have a crank arm, and we have a joint, and we have a piston. We can also solve this problem pretty quickly using an instantaneous center, where we know that the velocity point D looks like this, so the instantaneous center is perpendicular. If the velocity of B looks like this is also perpendicular. And so we have the angles, we do geometric construction, and we can determine what the velocity is of any point. Velocity point P is what we're referring to here. And so that's basically how it works. So to get back to the original statement, The instantaneous center is a technique. It only applies to velocity, and it only applies at one particular instant. The instantaneous center itself will rotate or will move in that locus of points, which is referred to as a centroid. But if you have instantaneous velocities, you can find the instantaneous center, you can find the instantaneous omega, and you can then execute problems where you find velocities at other points on the object using that principle. All right, that's it for section 15.3. We'll have another lecture for 15.4 coming up, where we'll get back into sort of the fundamentals of the kinematics of rigid bodies. Thanks.